We're doing repeated eigenvalues examples, and I want to clarify my language from before. This was a case of, here's a repeated eigenvalue. I said we only got one eigenvector out of it. We only got one linearly independent eigenvector out of it. Any scalar multiple of this eigenvector is also an eigenvector. So sometimes when I say you only got one, I mean only one linearly independent eigenvector. And we did another example where we had a repeated eigenvalue and we got two linearly independent eigenvectors, one repeated pair of eigenvalues. I went through that logic. I'm not going to repeat that. Let me do one more example of repeated eigenvalues. Here's a pretty bad looking A, and taking the determinant is pretty bad, pretty tedious. We'll just say a little elf came in and found the eigenvalues for us. The elf is otherwise known as the solution manual. But given that somebody gave us the eigenvalues, it's a repeated eigenvalue. A distinct one, lambda 1 equals 1, and then the repeated one, say 2. Let's see, lambda 1 equals 1. I'll subtract 1 from these diagonal guys. I'll get 2, 0, 0, right? The rest of them stay the same. Row ops, and they end up here. One row of all zeros, which I better always get. And for a distinct one, for a 3 by 3, I better only get one. Pivot, the free variable is K3. Each of these, this tells me K1 minus K3 equals 0, or K1 equals K3. This one tells me K2 equals K3. So set my free variable to 1, and I just get all ones. Okay. Now what about for the repeated variable? Subtract 2 from the diagonals. I'll get 1 minus 1 minus 1. All three rows are the same. So I'll have 2, all 0 rows. I'm going to get 2 linearly independent eigenvectors out of this guy. This says that K1's my pivot variable. K2 and K3 are the free variables. And this top row tells me K1 equals K2 plus K3. So I use the 1, 0 trick again. First set K2 to 1, K3 to 0, which means K1 is 1. And then set K3 to 1 and K2 to 0. K3, K1 is still 1. So there's another case of getting 2 linearly independent eigenvectors from repeated eigenvalues. One last thing to cover about eigenvalues and eigenvectors. You can get complex eigenvalues, and then you're going to get complex eigenvectors. As long as your A's are all real, which is all I ever dealt with, any complex eigenvalues are going to come in complex conjugate pairs, and so will the eigenvectors. I guess I'll say that without proof. In this case, what's minus 1 minus lambda times 1 minus lambda minus a minus 10, multiply that out to get this, which means I have complex, in fact, in this case, purely imaginary eigenvalues, plus and minus I3. So let's pick plus I3. That's our lambda. Minus 1 minus lambda is minus 1 minus I3. 2 minus 5, 1 minus I3. Take my word for it, or if we didn't make any mistakes so far, this second row is just going to be some complex multiple of the first one. So you do row ops, you're going to get a row of all zeros. And this is what you get, which tells me 2 times K2 equals 1 plus I3 K1. There's a sort of algebraic trick when you only have a 2 by 2. This right term, you could put it for the K1 term, and then minus this, the other guy, for K. I want to check this out. If I make K1 equals 1 plus I3, if I make K2 equals 1 plus I3, like that, I get 2 times 1 plus I3 equals 1 plus I3 times 2. So that does work out. I used a little algebraic trick I didn't quite teach you explicitly. But now that I have K1, K2 is just its complex conjugate. The 2 is all real, so its complex conjugate is 2. Complex conjugate of 1 plus I3 is 1 minus I3. You could have got them from the second row. It would have told me let's see, K2 equals 5, and then K1 equals 1 minus I3. And then K2 is its complex. So these are both legitimate answers, even though they look different. But take my word, one is just some complex multiple of the other. And that's all I'll say about complex eigenvalues.